today's class we will be talking about stacks, mainly about stacks. Besides that, we will also be talking about abstract data types, interfaces and exceptions, how stacks are implemented in Java, one application to the analysis of a time series. We will talk about growable stacks, do a little bit of amortized analysis, and then talk about stacks in Java virtual machines. Okay, so what is an abstract data type? So, it is basically a specification of what the instances are and what are the set of axioms that define the semantics of the operations on those instances. So, what do I mean by all of this? So, you know data types, for instance, you know integers, right, and you know real numbers and so on. So, when we talk of two integers and we say addition, so you understand the notion of addition. That is the same way as you add two integers in math, right. So, here similarly we will define data types in this course, and we will define certain operations on those data types, and those operations would be defined through what is called an interface, which is basically giving us what is called the signature of the operation. What are the parameters that the operation required, and so on. And then we will also specify what are the results of those operations through a set of axioms. Yeah, just as in the case of integers, you know the sum of two integers is as is defined in math, right. So, a plus b, if you had a variable of type a and a variable of type b and you sum them up, then you get the same answer as you would, you know, in your mathematics class. So, we will see examples of all of this, and perhaps that will be clearer then. The kinds of operations that we would be talking about would essentially be of three kinds. So, one would be just a constructor operation. So, this is the same as the constructor method in Java, right. You can, using this method, using this operation, you can create an instance of that particular data type. Yeah. So, when we are talking of sophisticated data types, this method will have to do a lot of work. Access functions which let us access elements of the data type, and manipulation procedures which would let us manipulate or modify the data type. Yeah. So, why are we talking about data types here? Data types help us identify what are the requirements, what are the building blocks of our algorithmic procedure, and what are the requirements out of those building blocks. It provides a language which will help us talk at a higher level of abstraction, right. We can talk in terms, just as we are talking of in terms of integers, adding to integers, we can talk in terms of maybe stacks or queues or any of the advanced data types that we will be discussing in this course. They encapsulate the data structure, which is how the data is organized, and the algorithms that work on that data structure. They encapsulate that, right, and they help us separate the issues of correctness and efficiency, and we will see more of this as I show you examples of data types. So, let me start by giving you a simple example of a data type, and that is a dynamic set. Yeah. So, you know a set as defined in your high school classes, right. It is a collection of objects, and suppose we also had operations which would let us modify that collection of objects, which means add an object to that collection or remove an object to that collection. So, such a set we would call a dynamic set. Dynamic because we are changing the set, right, we are changing the collection of objects, and we will create data types for such dynamic sets. Right. So, what are the kind of methods you would have in a dynamic set? So, you would have a method to create a dynamic set, that would be a method new, that would be this method new. There would be a method insert to insert an element into a dynamic set. So, S is a dynamic set, and this method has two parameters, let us say the set S and the element, and it gives as a result an instance of the set itself. So, it gives as a result a new set, another set which now includes the element V in it. Similarly, this removes the element V from the set S, right. So, these are two methods for updating the set. This is a method for constructing the set, and this is a method, one of the access methods. All it is telling us is whether this element is in the set or not. So, the result of this method, the return value is of type Boolean. If V is in the set, then it says true and otherwise false. Okay. And I talked about axioms which which tell us how these operations should behave, and we could write axioms in the following form, right. So, when I create a new set and I ask you, is V in the new set? When I create a new set, it is empty, there is nothing in the set, right. So, the answer to this should always be a false, no matter what V is. Yeah. If I have a dynamic set S and I insert an element V in it, now this resulting set has V in it. So, if I ask whether this set has V in it, then the answer to this should be true. If I have a set S and I insert U in it, then this resulting set now has U in it. Now, if I were to ask whether V is in the set, then what can I say? V is in this resulting set if and only if V was in the previous set, was in the set S. So, the answer to this operation should be the same as the answer to this operation, yeah, provided V is different from U. Yeah. Suppose I have a set S and I delete V from it, and now I ask you whether in this resulting set V is present, then the answer should be false. Yeah. So, these are some basic axioms that you can define which tell us how these operations should, what is the nature of these operations, what is the behavior, functionality of these operations. Yeah. Here we have not yet specified how we are going to do these operations. We have not talked of an algorithm, a procedure, or any such thing yet. We have, the least of all we have talked of any code for how we are going to implement the dynamic set, right. So, when we are talking of abstract data types, we are not interested in, we are interested in more of the specification, what the instances would be like, and what would be the operations that would be permitted on those instances, and what would be the axioms that govern those operations, that dictate that tell us what the operations are doing. Okay. So, some simple abstract data types that you are perhaps familiar with are queues. I do not know whether you know queues, but we will be doing that later in the course. Stacks, and stacks is what we will be doing today. Okay. So, let us get to stacks then. So, what is a stack? It is again a collection of elements, but now this collection follows what is called the last in first out principle. What this means is that the element which is inserted last would be the first to be removed. So, if I insert an element and then I say remove an element from this collection, then the element that would be removed was the one which was inserted the last. So, the operation of inserting an element is called pushing, and the operation of removing an element is also called popping the stack, right. And some of you might have seen this kind of toys. So, this just has the collection of elements. So, this could also be, for instance, a stack of trays in your mess. So, what you do when you put a tray, you put it on top, and when you remove it, you would always remove the one which is at the top. So, when you remove an element, when you pop off an element, it is always the one which you inserted the last. Yeah. Okay. So, this abstract data type, we are going to define it using, it is supported with these 4 methods. These are the key methods. So, new is a method to create a stack. Push, when I specify an element O, push adds this element O to this abstract data type. So, it inserts object O onto the top of the stack. Pop is not taking any parameter other than the abstract data type, right. It is just taking the stack as a parameter, and it says when I say pop this stack, it just says remove the top element from the stack. If the stack is empty, then this should flag an error. This should say that the stack is empty. Okay. The top operation returns the top element, it does not remove it. That is how it differs from push. So, that is how it differs from pop. Pop also removes that element. Top only tells us what is the top element. Yeah. Again, if the stack is empty, then top does not make any sense, and so it should flag an error. We can also have some support methods which will help us do these operations. So, size is one such method. So, size tells me how many elements are there in the stack, and is empty tells me whether the stack is empty or not. Yeah. So, everyone understands what the 6 methods are. So, we talked of push, pop, new, top, size, and is empty. Yeah. So, these are the methods. You understand what these methods are doing, and these are the axioms which govern the behavior of these methods, right. So, if S is a stack and I push an element onto S and then I pop the resulting stack, what should I get? The element that I pushed? No. Okay. So, when I pop, I should get back S. Okay. If I were to do a top operation now, so when I push an element V onto a stack and I do a top, I should get V, because V would be the top element of the stack then. So, this is as far as the abstract data type is concerned. So, we have defined what the stack abstract data type is. We have defined the methods, we have defined 2 axioms, maybe they are not complete, but this is what the axioms would look like. Yeah. Now, suppose we want to translate that into code. What do we do? How do you translate an abstract data type into code? So, for that we will need 2 constructs. Many of you might be familiar with this already, notion of interfaces and exceptions, right. And so, what is an interface? An interface is a way to declare what a class is to do. What are the various methods associated with the class? It does not tell us how those methods are done, right. That would be part of the implementation of that interface, the implementation of that class, right. So, for an interface we just write down the various names of the methods and the parameters those methods are going to take, and in fact, we do not even specify the names of the parameters, we just specify the types of the parameters. Yeah. When we write a class for that interface, we will actually provide the code for those various methods, right. I might specify an interface for a stack, and I am going to do that in a short while. Yeah. And I am going to ask you to implement that interface, right, write the classes for that interface. So, 2 of you could write different classes, you might implement the interface in completely different ways, but I can still use your classes, your implementations, provided they meet the specification, provided they meet the interface specification I have given you. Yeah. And I can use your classes in a program that I have written, or I can use any class, any implementation of that interface in the program that I have written, provided that implementation sticks to that interface. So, all I need to know is that this implementation meets this specification, meets this interface, and then I can use it in my own coding or in my own program. So, it helps us separate the implementation from the specification, and that is why it is a very useful programming technique. So, let us see what a stack interface would look like in Java, right. So, Java has a built-in stack data structure, but nevertheless we will define a stack interface here, and so as I said, we just define the various methods that are going to be part of this interface. So, there is one method called size. All I need to do is specify the types of the parameters and the return type of the method and stuff like that. Yeah, nothing more. I have not specified, I have not given here how these methods are actually implemented. This is just an interface. your question is whether in an interface we need to know the type of,
like the parameter types of the function.
yeah. So, we need to know the types of the parameters, yes, as is here. So, when I am pushing, so it takes a parameter of type object, right. Object is this generic type in Java, all objects are derived from this type. Okay. So, for instance, the method is empty returns boolean, right. That just tells us whether the stack is empty or not. Recall that top gives you the top element in the stack. So, it returns an object, and we also have this it throws stack empty exception. So, we said if the stack is empty, then this method should somehow signal that, right, and we are going to do that using the notion of exceptions, and I come to that in a minute. Okay. So, what is an exception? Exception is another.
In the last slide, what does the void thing mean?
Void means it does not return. It does not return any object or any value.
But it does. It returns the actual. It returns the original stack with the new element. Doesn't it return the new stack?
Right. So, it does not return a stack. It is a method which is executed on the stack. It modifies the stack.
So you basically don't consider stack as a parameter.
You don't consider stack as a parameter here, exactly. Okay. So, exceptions are a mechanism to handle errors. So, when we have an error, so when we reach some exceptional condition or an exceptional case in the execution of a program, we throw. So, the Java term is throw, we throw an exception. So, as soon as an exception is thrown, the flow of control moves from that current method to the method to the point where the method was called. Okay. And I will soon show you an example of this. The idea essentially is that when an exception occurs, when something exceptional happens, you delegate the responsibility of handling that exceptional case upwards. You delegate the responsibility of handling that problem or that error to the procedure which called this particular method. Okay. We see examples of it, and that will be clear. Okay. I have two methods here. One is an eat pizza method, which throws a stomachache exception, right. So, there is some code here and there is some dotted code here. So, if you ate too much pizza, then there is a problem, and so you throw a stomachache exception here. This procedure eat pizza was called here in the simulate meeting procedure. So, here I called this method eat pizza. Yeah. So, when this exception is thrown, the flow of control will come to this point. Yeah. Okay. So, when this exception is thrown, we will exit this method eat pizza and go to this point.
Sir, there is another statement after this exception, after this throw line. Would it get executed or it?
No, it would not get executed. If there were, so your question is if there were other statements after this, and there are other statements here, I have not shown all the statements. These dot 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 means that there are a bunch of statements after this, they would not get executed. The flow of control would interrupt at this point and would now reach here. Okay. Now, there is also this notion of try and catch blocks.
So, in case there may be some variables which we have modified. So, suppose before exception was thrown, the variables have been modified by this method. So, once it throws the exception, once the exception is handled, so when it reaches back, will the variables will be in their modified form or will they be in the original form?
So, it depends. So, your question is that when exception is thrown, what happens to the variables that we might have modified here, right. Now, again it depends upon, it is like a procedure call, right. When you return from a procedure, think of it as if you are returning from this procedure here at this point, returning from this method. So, if those variables were local variables, then you do not see them here. If there were some global variables, then if they were modified here, those modifications get carried over at this point. Right. Now, there is something called a try and a catch block here. So, if you thought that there could be a possible exception in this method, then you enclose the method within a try block. So, try bracket whatever method you are calling and close bracket. Now, if there was no exception that was raised in here, or if this particular exception did not get raised in this method, then we will just skip this catch block and go on to the statement after the catch block, which means something here. But if an exception was raised in this method, in particular this exception was raised in this method, because this method might raise many exceptions, right. If this exception was raised in this method, then we would come into this catch block and execute the statements here. Does everyone follow what I am trying to say? Right. So, if the method raises an exception, then if that exception is getting caught here through a catch block, then we would do whatever is written in this, execute whatever statements are written here. Now, what are the statements written here? Here you could have any kind of, so you do not necessarily have to have a system.out exception. So, here is a slide where I have tried to explain this.
In the previous thing, if we don't have to write a statement when we catch that exception,
yeah.
so what does the loop this program do?
So, your question is, if I did not write this catch block at all, if I did not write this catch block, what would have happened? So, what would have happened then is that this procedure simulate meeting now would throw the exception to its parent procedure wherever it was getting called from. So, when this throws an exception, this will also throw an exception. The control will go to where simulate meeting was called from. If that at that point I am catching this exception, fine. If not, it will throw an exception to the higher level procedure and so on, and finally your procedure will stop with your exception finally appearing at your console, right. So, in this manner it will keep getting propagated up all the way till your procedure stops and the exception is then shown to the user.
So, what does this out signify?
This is just a method to print out the statement.
So, that stomach exception.
Oh, so an exception can so we will see that in the next slide. An exception is really a Java class, right, and by doing this I am creating an object of, and I am creating an instance of this class, and I am initializing that instance with any parameter that might be specified here. So, I can specify some set of parameters here, right. So, a stomach ache exception itself is a class, and I am creating an object by making this call. I am creating an object of this class.
Isn't E the object?
Yeah. So, when this is caught, this E would get assigned the object that is created by this statement.
Sir, if there is an exception, if an exception is thrown, would we are not enclosing it in a try box, try block?
Yeah.
Then straight away the exception would come on the console.
No, again it will be moved up to the calling procedure.
We are not trying it.
Yeah. So, actually, yeah. So, if it was not enclosed in a try, so this try and catch come together, right. But if you had not enclosed it in a try at all, then it would, that exception would just get propagated upward, move upward in the procedural hierarchy, right. So, if this there was this exception was thrown, then this procedure would throw an exception and its calling procedure would throw an exception till it gets caught at some point. If it does not, it reaches the console.
So, a class name, then a bracket followed by like within the bracket this ouch is written. What does that signify?
That signifies creating an object. So, your question is a name of a class followed by brackets and some parameters written here. What does that signify in Java? In Java, that signifies that you are creating an object of this kind, of this class. You are invoking the constructor method for this class with these as the parameters. Okay. So, I have just put this down on a side, the try and the catch block are a method of listening for exceptions and catching them. So, as I mentioned before, a catch block can contain anything. It does not just have to have a system.out.println. It can also throw an exception in turn, but it can also do other things to help you gracefully exit from the program when an exception happens. So, if you throw an exception in any method, then you need to add a throws clause when next to the method name, as we did on one of the previous slides. Right. So, when we wrote the method eat pizza, we had throws this exception.
So, can we use more than one exception?
Yes, a method can throw more than one exception.
So, what did you mean by the stomachache exception itself being a class?
I come to that on this slide, right. So, when you are defining a stomachache exception, what is a stomach? So, in Java everything is really an object, right. So, stomachache exception here is the name of a class, okay, and this is the constructor method for the class, right. Recall that the name of the constructor method is the same as the name of the class. So, the constructor method here is taking a single parameter, which is a string, yeah, and what does super mean? It is calling the super class with the same, with this parameter then. So, again as I mentioned before, if you never catch an exception, it will propagate upwards along the chain of method calls till it reaches the console. Any questions?
What calls the constructor of the parent class?
It calls the constructor of the parent class, the class from which this class is getting derived. Since stomachache exception is extending runtime exception, it will call the constructor method for the runtime exception.
What do you actually mean by class in here? We can define classes as integers and something, but what is this stomachache exception you can call a class? And how can it call some other class?
I think I am going to pass that question, because that it seems to me that you need to understand a little bit more of Java before, right. So, we will not take this question here. Yeah.
So, if it's trying more than two types of exceptions,
Yeah.
so what will the throws call? We have to write both?
Yes. So, if a particular method throws more than one exception, then you will have to specify all those various exceptions it can throw next to the name of the method. Yeah. And then even in the try block, you can have many catch statements, right. You can have catch this exception followed by catch some other exception followed by catch a third exception and so on. Yeah. You need to look at your Java book for these things. So, now we get back to our stacks. So, we had created the interface for a stack. Yeah. Now, we are going to implement methods, and there can be many ways of implementing a stack, and the first way we are going to discuss here is using an array. So, I am going to have an array. Let us say the maximum size of our stack is capital N. So, I am going to have an array of n elements. This is going to contain the elements, this array is going to hold the elements of the stack, and I am going to have a variable t, which will tell me where the top element of that stack is. Yeah. So, t gives me the index of the top element in the array S. So, the first element will come at location 0. When I push another element, it will come here. When I push another element, it will come here, and so on. So, here I have actually listed out an entire implementation for our stack interface. So, my implementation is called array stack because I am using an array to implement this stack, and this statement says that it is implementing the stack interface by saying array stack implement stack.
So implement stack means it is implementing the stack interface which we have provided earlier.
Exactly. By implement stack means it is implementing the stack interface we have provided earlier. And I have set a default capacity for the stack, which is, let us say, 1024. Otherwise, the capacity of the stack would be in this variable n.
What is this final mean?
Final is just specifying that this is a constant which its value can never be changed. Right. S is declared to be, so S is that array which is going to hold the elements of the stack. So S is an array of objects, and T is the index of the top element. So T is initially -1 because there is nothing in the stack. Right. T is equals 0 means the top element is at location 0. So when the stack is empty, T is -1. Right. And these are two constructor methods. If you don't specify anything, if you just call array stack without any parameters, then I am going to create a stack whose capacity is 1024. And if you call array stack with some number, let us say 37, then I am going to create a stack of size 37.
So can you please go back to the previous slide?
Okay, now given this, the method should be very easy, right. So what should size do? So size should just return how many elements are there in my stack. So if T is the index of the top element, then how many elements are there? T plus 1, because we started from 0. So if you want to know whether the stack is empty, the stack is empty if T is -1, less than 0. So if T is less than 0, then the stack is empty. So if T is less than 0, this method would return true, otherwise it would return false. If I want to push an object into the stack, I am trying to push this object into the stack, then if the size of the stack already equals n, then I should throw a stack full exception. Else I should first increment T and then put the object at the new location, the incremented location. Yes. So this is first increment and then put the object at that location. I have to give you the top element of the stack. So what should I do? I should first check if the stack is empty or not. If the stack is empty, then I throw a stack empty exception. As recall that if the stack is empty, then the flow of control would exit from here, right. So if the stack is not empty, then I just return the top element of the stack. If I want to pop the stack, then once again I check if the top element is empty. So if the stack is empty, if the stack is not empty, then I, let us say, save the top element in location element. I decrement T because I am removing the top element, and let us say I set the what was T earlier, that index at that location, I set a null, I dereference it, right, because earlier at the top location, at location T, at location number T, there was let us say T was 37 initially, right. So at location 37 I had an object, so I need to remove that object and I need to decrement T to 36. I am doing that here, and then I return the top element. Pop returns the top element also.
So what does this new mean? Like new we generally use to allocate memory.
Yes. So recall I said stack empty exception is a class, and I am creating an object of this type of class. I am creating an instance of this class, so I need to use new.
So like we are setting the element we are deleting to null, but usually in general we never we just move the top pointer down and we don't set it to 0.
You can also do that. So he is saying, why should we necessarily dereference it? You can also do that, but it's best to to actually dereference so that you can remove those objects, so you can get rid of those objects, right? Otherwise they will lie around in your memory.
Once like that, to the declaration of variables, like the first stage of the implementation. of stack in Java, which we did this one. This one we are making int t, private int t is equal to -1. This t is a member of the class, a variable in the class.
Yes.
So it is not a static object. So it could be implemented only by an object of the class array stack.
Yeah.
So if we are writing straight away as st, that means we are using the numerical value of t. But we need an object whose member t we will be accessing, isn't it?
I do not think I even understand your question. Okay, but I think what you're trying to say is, okay, or let me clarify what this here is. T is just an integer, okay, and it is a private member of this class, private because no one else needs to know about T, and S is an array of objects, and ST can therefore then access the tth element of this array. Okay, we will take your question later then. Yeah, I will continue. So, about the array implementation, it is very simple. All the operations were taking constant time. None of the operations required time proportional to the, which was dependent upon the number of elements in the array, in the stack at that point, right. So, each of those methods take order 1 time. The problem, however, is that we are working with an upper bound on the size of the stack, right. So, this upper bound was either we took the default value, which was 1024 in our example, or it was specified at the time of creation of the stack. Why is this a problem? You know, we do not know quite often beforehand what size stack we should have. We might allocate a very large size stack, in which case it might be a waste of memory, or we might allocate a very small stack, in which case we might not be able to run our procedure to completion, because we will soon have a stack full exception, right. So, stack empty exception is a requirement of the interface. Why do I say this? Because the top and the pop methods are not defined if the stack is full, the stack is empty. So, it is a requirement of the interface really, but a stack full exception is an artifact of this implementation. If I had some other way implementation perhaps, then I would never have to even raise a stack full exception, and we will see an example of this. We will see how we can implement the stack so that we never have to make a stack full exception, so that we can always grow the stack when need be. You have a question? You have a question? Okay. So, we will look at an application of stacks very quickly. We have the stock prices for, we have the daily stock prices of, let us say, a particular stock. So, I give you the price on day 0, the price on day 1, the price on day 2, 3, 4, 5, 6, so on. The span S sub I of a stock price on day I is defined as the maximum number of consecutive days that the price of this stock has been less than or equal to its price on day I, right. So, this example would make it clear. So, the span, so S5 is the span of the stock's price on day 5, and it is equal to the maximum number of days that the price of this stock has been less than or equal to this price. Yeah. So, for 4 days the price of this stock was less than or equal to this day's price, and so the span of the stock's price on day 5 equals 4.
Inclusive of the current day.
Inclusive of the current day. So, this picture should make it clear, right. So, we are counting 1, 2, 3, 4, and for here instance for day 6 it is 1, 2, 3, 4, 5, 6 days, right, and for all others it is, so this it's 1, this it's 1, this it's 1, this it's 2, right. So, how can you compute the span? So, I give you the stock prices in, let us say, an array P. So, P is an array of numbers, I give you the stock prices in this array and I want you to compute the span in an array S. Right. So, what is it that you are going to do? So, to compute S sub I, what you are going to do is you are going to look at the price of the stock on day I, look at the price of the stock on day I minus 1, I minus 2, I minus 3 and so on, right. So, k, the index k will start from 0 and keep going down, and you will keep going down till the price of the stock on day I minus k is less than the price of the stock on day I. The moment you find a case such that the price of the stock on day I minus k is actually more than the price on day I, you stop this loop, right. Otherwise, you keep incrementing k. So, if this quantity is less, then you increment k, else you say done is true. Done will help us exit this repeat until loop. They will exit the repeat until loop if done is true, or if k equals I, which means that we have reached day 0, right. And what will be the span then? The span then will be determined by the value of k, because k then tells me what is the span of the stock's price on day I. So, S of I gets the value k. Yeah. So, this would be one way of implementing this, doing this thing, computing the span. Now, how much time does this take? You can see on the slide it says n squared, so it should take n squared time. Why should it take n squared time?
We are repeatedly comparing it.
Exactly. So, this loop could in the worst case go all the way from, so how many times could this loop be executed in the worst case?
From ith position to 0,
I times, right, and I is varying itself from 0 through n minus 1. So, once again we have the same summation as we saw in the last class. So, this is executed I times and I is going from 0 through n minus 1. So, the total number of times this might get executed, one of these statements might get executed, might be n squared by 2 roughly. Yeah. And so, the running time of this algorithm is big O of n square in the worst case. So, question is, can we do something better? Yeah, and quite likely we can, which is why we are talking of stacks. So, we can use a stack to do something better. So, recall that to compute the span, we need to know the closest day preceding I on which the stock price is greater than the price on day I. Yeah, that is what we need to know. So, in this example, I need to know for day 5, I need to know the closest day preceding day 5 on which the stock's price was more than the price of day 5. So, this was the price on day 5. So, on day 1 it was more. Yeah. So, for day 5 the span would be 1, 2, 3, 4. So, I am going to call this quantity h of I. What is h of I? H of I is the this quantity here, closest day preceding I on which the price is greater than the price on day I. Yeah. So, who can tell me what is h of 3? H of 3 is 2, h of 2 is 1, h of 1 is 0, h of 0 is minus 1 conventionally, let us define it that way. H of 4 is 3, h of 5 is 1 and h of 6 is 0. Once you have computed these h's, how can you determine S sub I, the span? The span is then just given by, so what is span of 5 then? Span for the price on day 5 is 5 minus 1, 4. Yeah. So, if we can compute these h quantities, we can compute what the span is very easily. How do we compute the h quantities? Suppose these were the prices that I had given you on days 1 through 6. I have not told you what the price on day 7 is. Okay. But can h of 7 be 1? I have not told you what the price on day 7 is, but what is h of 7? Our definition of h7 is the closest day preceding 7 on which the stock's price is larger than the price on day 7. but that day cannot be 1 at all, because the price on day 2 is larger than the price on day 1. Similarly, that day cannot be 3 or 4. Yeah. So, what are the possible values that h of 7 can take? 2, 5 and 6. These are the only possible values that h7 can take. I do not know what h7 is, but these are the only values it can take. Yeah. So, we will store these indices 2, 5 and 6 in an array, in a stack. 2 will be at the bottom of the stack, 5 will be above that and 6 will be at the top. Yeah. Now, to determine h of 7, what do I need to do? I will first compare the price on day 7 with the price on day 6. Suppose the price on day 7 was less than the price on day 6. Then what is h of 7? 6. But if the price on day 7 was larger than the price on day 6, then I will compare it with price on day 5. If it was larger than the price on day 5, then I will compare it with 2. If it was larger than 2, then it is minus 1. Then h of 7 is minus 1. So, suppose this is the price on day 7, this new bar that I have drawn here. So, now it is more than the price on day 6. So, what is h of 7 then? 5. Right. So, h of 7 now becomes 5. So, the first price larger than the price on day 7 in this comparison gives me h of 7. But now once I know h of 7, I should update my stack. What should my stack contain now? Earlier it contained the indices 2, 5 and 6. What should it contain now?
2, 5 and 7.
2, 5 and 7. Is that clear? Because for 8 now, h of 8 can never be 6. So, I should get rid of the 6 and replace it by 7, right. So, you can see that a stack would be the right way to do these things, and let us look at the procedure which does this now. So, D is going to be the stack of mine. Okay. Initially it is empty, and what am I going to do? When I get a certain price, I am going to compare that price with the price on the top of the stack. If it is less than the price on the top of the stack, then what happens? Recall the previous picture. If it is less than the price of the top of the stack, so on the top of the stack we had 2, 5 and 6. If this bar was less than 6, then it is just what is there on the top. Then we are done, right. The index on the top of the stack will give me my h value, right. If it is more than the top on the stack, the price on the top of the stack, then I will pop off, I will remove the top of the stack, because now I need to compare with the next one. And why can I pop off? Because I will not need that quantity anymore later. As you recall from the previous slide, since this was more than this, I can actually get rid of this, because next time in the stack I do not need this 6 at all. Yeah. So, we are going to do this pop. So, we are going to go around in this loop till either done becomes true. When done becomes true, that means I have found a price which is larger than the current day's price. But if done never becomes true and the stack becomes empty, then what happens if the stack becomes empty? H is minus 1. So, exactly that is being said here. If when I exit this loop the stack is empty, then h should be minus 1. Else what is h? H is the top value of the stack. Yes. And once I know h, I can compute s of I, and I keep this in. And I will push this I back in now. Yeah. Recall in the previous slide, when I got this 7, I now push 7 in for my next computation. Great. So, how much time does this take now? Why should it take n? Maybe this loop executes a whole lot of times. This while loop might execute a lot of times. So why should this take only n time?
But it can execute only once, then it will become single time.
So the worst case is again is n squared, because if we get an increasing order, then
So is the worst case n square or is the worst case n here?
N square.
N square.
N square.
How many elements do we ever push on the stack? One. No. In all, how many elements do we push on the stack? Each element is pushed once. So, in all we are pushing at most n elements on the stack, if there are n elements to begin with. Every time this loop is executed, yeah, we pop off one element from the stack. Yes or no? Yes. So, how many times is this loop executed overall? Huh? At most 10 times. Every time this loop executes, we are removing an element from the stack. So, if the total number of elements we ever pushed on the stack was n, then how can I pop off more than n elements from the stack? So, that means that the total number of times this loop executes is not more than n, right? And how many times do these statements execute? They all execute at most n times, because this is part of a for loop. This executes exactly n times, this also executes exactly n. So, what is the total number of total time you will take? Order n, not n square. I hear some of you still saying n square. I am saying the total number of times this loop executes over all iterations put together is no more than n, because every time the loop executes, every time we go through this loop, we remove one element from the stack, right? And we never push more than n elements. Total number of elements we ever push on the stack is at most n. Okay,
so what was k in the last algorithm? You assigned k as 0 in the beginning.
Good question. I don't seem to know what k is. It should be h. Yeah, this k should be h. Thank you. Okay, so I said one problem with our stack implementation so far was that we had to give a maximum size for the stack. Yeah. Suppose so now we are going to look at an implementation in which the stack can grow if it ever gets filled. Right? How are we going to do that? If the size of the stack, so when we are pushing an element, if the size of the stack is n, then I create a new array of length f of n. We will come to what f of n is. I create a new array, I copy all the elements of my original stack S into A, and then I rename A as S. So, this becomes my new stack. So, I now have a new stack which has f of n elements in it, f of n locations in it, which has capacity f of n. F of n will be larger than n for us, and so we would have increased the size of the stack. Okay. And I increment and I do the regular thing that I need to do for a push, that is I increment the top counter and I put the object that I am trying to push at this top location. So, question then is what should we choose f of n as, right? So, there are two strategies that one could adopt. One could either have a tight strategy or a growth strategy. In a tight strategy, we always increment the size of the array by some constant c. We just increment, additive increment, and in the growth strategy we double the size of the stack. अगर पहले 10 था तो अब 20 हो जाएगा size of the stack. And we want to compare these two strategies. We want to see which of these strategies is the better strategy. So, we are going to think of pushes as of two kinds. One is a regular push. In a regular push, there was space in the stack and you just push the element. So, it takes 1 unit of time. A special push is one in which the stack was already full and you had to create a larger stack and copy the elements from the earlier stack to this larger stack and then push the element. So, you created a stack of size f of n that costs f of n units. you copied the n elements, that costs n units, and then you push that one more element, so that costs 1 more unit. So, total cost of this special push operation would be f of n plus 1. Okay, so let's see how the tight strategy, which is where we are incrementing the size of the stack by c units, where c is now, for this example I have taken c to be 4, how this behaves, right. So, initially I started with a stack of size and with the array of size 0. When the first element came to push, that was a, then I created a stack of size 4, right, and I pushed this first element in. So, the total cost was 4 plus 1. When the second element came, I do not need to enlarge my stack because I have space, yeah. So, it just cost me 1 unit, it is a regular push. This is also a regular push, this is also a regular push. So, they all cost 1 unit each. Now, this is a special push because when I am now trying to push E, this stack is already full. So, I need to create an array of size 8. I need to copy these 4 elements in there, that is the 4, and then I need to push 1. So, the total cost becomes 8 plus 4 plus 1. So, these are all 3 are next regular pushes, and then once again when I fill this, I will create an array of size 12 now. Why? Because C is 4. So, I am incrementing the size of the array by 4 units every time. So, I create an array of size 12, I copy these 8 elements and then I push this one more element. So, I get 12 plus 8 plus 1 and so on, and finally, I have this thing. So, I am going to call this one when the size of the array was 4, I am going to call that phase 1, when the size of the array was 8, I call that phase 2, and so on and on, right. And let us see what is the total cost that we incur in this procedure. Okay, so there is a small problem here. This pound is a multiplication operator. So, think of this as multiply, right. So, in phase I, the size of the array is C into I. Yeah, in phase 1 it is C, in phase 2 it is 2C, in phase 3 it is 3C, and so on. So, the size of the array is C into I. So, what is the total cost of phase I? At the beginning of phase I first create an array of size C into I, then I copy the previous array, then I copy the elements of the previous array. So, look at this example here. I first create an array of size 8, I copy the previous 4 elements. So, I copy C into I minus 1 elements is the cost of copying the elements into the new array, and then I will do C more pushes into this in this phase, a total of C more pushes in this phase, right, before the array gets full. So, I will do C is the total cost of the 4 regular pushes that we would be doing, C pushes that we would be doing. And so, the total cost is C into I plus C into I minus 1 plus C, which is 2 times Ci. This is the cost of phase I. In each phase I am doing C pushes in all, right. So, if I have to do a total of n pushes, then how many phases do I need? N by C phases roughly, and total cost of these n by C phases would be 2C times 1 plus 2 plus 3 all the way up to n by C, because the cost of the ith phase is 2Ci. And what is this quantity? This sum is roughly n square by C square times 2C. So, it becomes, this is approximately, so this is not a T, this is approximately order n square C, or this is equal to order n square C. Right. So, this is as far as the tight strategy is concerned.
So, what do you mean by cost? Is it the time cost?
Yes.
Yeah, time.
But then how creation of an array costs that much? Like if you create an array of size 8, how is it costing you 8 units? Why not creation is order 1?
We could also take creation as order 1, right, in which case this analysis would change slightly, right. For the purposes of this analysis, I am just taking it as, if you are creating an array of size something, you take that much as the cost. Okay. So, let me quickly run through the growth strategy, we are running out of time here. So, in the growth strategy, I start with an array of size 0. When I get the first element, I create an array of size 1. When I am trying to push the next element, I would double this array. So, I create an array of size 2 and I push this element. When I am trying to push the third element, I double this array, I create an array of size 4 and I push this element. right. Then I have space for one more. So, this is a regular push, pushing of D. When I am trying to push the fifth element, I will double the size of the array again, right. So, I create an array of size 8, copy these elements, and then I push the fifth element, and so on and on, right. So, once again we can analyze the cost. One is the cost of creating the array, you do not have to copy anything, and one is the cost of pushing them. Here we created an array of cost 2, we copied one element, and 1 was the cost of pushing. We created an array of size 4, 2 was the cost of copying, and 1 was the cost of pushing the element C. Here this was a regular push, so this was 1, and so on and on. And once again we define a phase as when the cost of the when the size of the array was 1, we call it phase 0. When it was 2, we call it phase 1. When it was 4, we call it phase 2. When it was 8, we call it phase 3, and so on. So, as you can see, in phase I, the array has size 2 to the I. Phase 3, it has size 8. Phase 4, it has size 16, and so on. So, in the phase I, since it has size 2 to the I spend 2 to the I units of time in creating the array first. Then I have to copy the elements of the previous array, right. So, that is 2 to the I minus 1 elements of the previous array, they have to be copied. So, how many elements are left after copying the 2 to the I minus 1 elements? 2 to the I minus 1 elements are still left. They have to be pushed in this phase. So, 2 to the I minus 1 is the cost of pushing in those 2 to the I minus 1 elements. So, the total cost of phase I is 2 to the I plus 2 to the I minus 1 plus 2 to the I minus 1, which is 2 to the I plus 1. If we do n pushes in all, how many phases would we have? We would have log n phases, right, because of the way the array is growing. So, the total cost of the n pushes is going to be 2 plus 4 plus 8 and so on up to 2 to the log n plus 1, which if you sum this up is 4n. So, the total cost of n pushes is 4n here, and what was it in the case of the tight strategy? N square by c. So, this is clearly a better strategy. Right. With this, we are going to stop our discussion about stacks. The next class we will discuss queues and linked lists. Stop here then.